Okay, so we're going to talk about three-phase power factor correction, and then we are finished. So we hopefully recall that for a single phase steady state sinusoidal circuit, C was equal to negative Q cap divided by omega times VRMS squared. Or alternatively, P tan theta old minus tan theta new over omega VRMS squared. These relationships still absolutely work in a three-phase circuit, but the distinction here we talked about at the end of the last class period was that there are now going to be three capacitors in a bank. So let's work an example, kind of feel out what the relationships are. So let's say that I have a balanced three-phase source where we have a line-to-line voltage of 400 volts RMS at a linear frequency of 50 hertz. And this source, let me give myself enough room here, feeds a balanced three-phase load that absorbs, let's say, 50 kilowatts per phase at a power factor of 0.8 lagging. Okay. And we want to know the value of the capacitors in both a delta connected capacitor bank we'll call these guys C delta, and the values in a Y connected capacitor bank that would correct the power factor to 97.5%. So we want to know, to be clear here, CY and C delta to correct power factor of the load to 97.5% lagging. Give me just a minute. I need to go grab a calculator. Second. All right, sorry about that. I have three of these damn things, three of these and three of the Casios, and I never seem to remember to put one in my bag. Excuse me. All right, so excuse me. All right, so which do you want to do first, the delta capacitance or the Y capacitance? Delta, okay, sounds perfectly reasonable. So we know that C is equal to the average power, P, multiplied by the tangent of theta old minus the tangent of theta new divided by omega VRMS squared. Which of these quantities do we know? So actually, so I'm going to call this C delta here. All right. So you say that we know what VRMS is. So what is it? Yeah, so in this case, since we're looking for the delta connected, the parameters for the delta connected capacitor bank, that would be the RMS voltage would indicate the line voltages, which is exactly what we're given. So you're 100% correct there. So we know that that is 400 volts RMS. What about omega? Yeah, so I would argue that since we know our voltage is operating at a frequency of 50 hertz, omega is going to be 100 pi radians per second, since we just multiply the linear frequency by 2 pi. What about the average power?
They give that to us.
50 kilowatts. All right. So this is 50 kilowatts per phase, which is exactly what we're looking for. If we were told instead that our load absorbed a total of 150 kilowatts over 3 phases, we would actually need to convert it down to a per phase basis, because each capacitor is only going to correct one phase of the system. So we absolutely need to have our average power in this case on a per phase basis, which is exactly why I gave it to you like that. So we would know that P is 50 kilowatts. So the only two other pieces of information that we have to figure out is theta old and theta new. And I think that we have enough information to get that pretty easily, right? So theta old would be, sorry, not the inverse tangent, the inverse cosine, right? Of the old power factor, which I think is going to be 36.87 degrees, but let me double check. Cosine inverse of 0.8. Yep. 36.87 degrees. Theta new is going to be the inverse cosine of the new power factor. So that would be inverse cosine of 0.975 or 12.838 degrees. So with that taken care of, we actually have all of the information that we would need to calculate C delta. So that would be 50 kilowatts times tangent of 36.87 degrees minus the tangent of 12.838 degrees divided by 100 pi radians per second multiplied by 400 volts RMS squared. And I get this to be 519.34 microfarads. So how do we go about calculating CY? What's the only quantity that's different? Exactly right, the voltage. What is the voltage going to be? So let's do our equation for CY here. Right? So P is going to be exactly the same. Tangent theta old minus tangent theta new, exactly the same. Omega is exactly the same. But how's this VRMS going to be different? Right. So we're going to convert our line voltage to a phase voltage because our Y connected bank now has a line to neutral voltage across it. So that would just be VL over the square root of 3 quantity squared, which is literally just going to be 519.34 microfarads divided by a factor of 3, or 173.113. So I think you are correct. So The question for the one person who's on Zoom who isn't me is since we have a factor of square root of 3 squared in the denominator of the denominator, I think you're correct that it actually should be multiplying by a factor of 3. Yes. So 3 times 519.34 microfarads. So that would be that times 9. So that would be 1.558. Thank you for that correction. That's the only difference between the Y-connected capacitor bank and the delta-connected capacitor bank, is that you're going to have that voltage. Either if you're given a phase voltage, you're going to have to multiply it by a factor of square root of 3. And if you have given the line voltage, you're going to have to divide the voltage by a factor of square root of 3, which winds up being multiplying and dividing the capacitance by a factor of 3. Does that make sense? Well, it's a delta Y conversion on a capacitor bank, right? Which is just an impedance. And we know for a balanced Y-connected load or Y-connected impedance and a balanced delta-connected impedance, to convert between those two, it's multiplying or dividing by a factor of 3, right? It actually goes in the opposite direction that we would think it would go, because capacitors, their impedance is inversely related to the frequency, right? It's negative J over omega C, or so it's inversely related to the capacitor value. So to go from delta connected capacitor to a Y connected capacitor, we multiply by 3 because of the inverse relationship with the capacitors. Yeah. So that's it. Class is done. I mean, we can do more of these or whatever, but for the most part, the equations that we're using here are the exact same things that we developed for single phase power factor correction. And we could easily treat this as single phase power factor correction problem by looking at a single phase equivalent circuit and then going from there. So I can beat this horse further to death if you want, but I don't see the point.
Yeah.
Sure. Yeah. If you got questions, by all means, let's cover some stuff.
I feel like I don't really maybe
Okay.
look to see. Okay. Maybe one of these again where it's like with the delta and a Y and what or like
Okay. Sure. So you want me to just make up an example, or you want to work a homework problem? Because I think there's a homework problem or two like that, or. Let's see. Let's look at homework set. Let's see. This is ELEN 223. Spring 2021. Homeworks. Let me scroll down here to the bottom. Did I not? This isn't spring, it's summer. That's why those aren't showing up right. There we go. So homework 17, problem 5. I think that's actually the exact example problem that I worked in class. So let's not do that one because that's pointless. So problem 5 here, balanced 3-phase system, ABC phase sequence, We have a delta connected source and then two parallel Y connected loads. And we want to find the delta currents in the source. That sounds like it will be helpful if we take a look at it. Okay. All right. I don't think I can just copy this over. So I'm just going to draw our circuit on the other thing here. All right, so let's see, we have a delta connected source and then two parallel Y loads. So our delta connected source A, B, C. This would be VAB, BBC, VCA. We have some transmission line impedance, W. Then we have two Y connected loads in parallel. So I'm going to call this ZY1 and parallel ZY2. And here's our third one. So let's see, what were the parameters of our system? We are told that ZY1 is 4 plus J4. ZY2 is 10 plus J4. ZW is 0.3 plus J 0.2. And IAN1 is 10 angle 20 degrees amps. This is capital A, capital B, capital C. Our goal is to find the delta currents in the source. So let me define exactly what I'm looking for. So the delta currents in the source would be the phase currents in the source, since it's a delta connected source. So that would be this current here, IAB, this current here, IBC, and this current here, ICA. And legitimately, we might not even have to go to our single phase equivalent circuit for this guy. And I say that because I feel pretty strongly that we can get there using only Kirchhoff's current law-based relationships. So that phase current that we know, IAN1, is this guy right here. We do not know IAN2, but I think we can figure it out. And our intermediate step, I believe, is going to be figuring out what this line current IAA is. And then I think that'll give us enough information to back solve for those delta currents in the source. So at present, we know this guy, right? So how would we go about figuring out what IAN2 is? Right. Sure. So since we know what the phase current IAN1 is, I don't think I wrote the one here. We can use Ohm's law to figure out this voltage. VAN, right? So we could say VAN would be IAN1 multiplied by ZY1, which would be 10 angle 20 degrees amps RMS multiplied by 4 plus J4 ohms. I think is going to be 40 square root of 2 angle 65 degrees volts RMS, if my mental math is correct, but I'm going to double check that. 10 angle 20 times 4 plus 4i. Yep, 40 square root of 2 angle 65. I'm not some kind of crazy math savant. I know that whenever I have the same real part and same imaginary part, it's just going to be that guy multiplied by square root of 2, and that the angle is going to be 45 degrees. So I'm not some weird, insane person that can do complex math in my head. So just feel like I need to say that. All right, so from here, IAN2 would be VAN divided by ZY2. So our 40 root 2 angle 65 degrees volts RMS divided by 10 plus J4 ohms. I get to be 5.252 with an angle of 43.200 degrees amps RMS. From here, our line current IAA would simply be IAN1 plus IAN2 or and angle 20 degrees amps RMS plus 5. That does not look like a 5.252 angle 43.2 degrees amps RMS. I get to be 14.971 with an angle of 27.943. And now I'm going to have to apply Kirchhoff's current law up here, right? So I'm going to apply KCL at this node that I've just circled in red. So I know that IAA, my line current, is leaving. ICA, my phase current is entering, and IAB, my phase current is leaving. So just so I don't mess this up too much, I'll write everything out. So we have IAA plus IAB is equal to ICA, which we can rearrange and say that IAA, our known quantity, is negative IAB plus ICA, which looks like IAB multiplied by 1 angle 180 degrees. So that's me taking care of my negative sign. Plus 1 angle negative 240 degrees, because I know that the C phase lags the A phase by 240 degrees. So rearranging, I would find that IAB is IAA divided by 1 angle 180 plus 1 angle negative 240. And that gives me 8.644 with an angle of negative 122.057 degrees amps RMS. So what I'm trying to figure out in my head, I know that the magnitude has been divided by the square root of 3 for sure. What I'm trying to figure out is what the phase shift here is, and it looks like it might be 150 degrees, the way that things added up, which would make sense because there's going to be a phase shift on 120 degrees, and then there's also going to be a 30-degree shift to go from that line to neutral quantity. So anyhow, so anytime we have those conversions, it's always going to be some integer multiple of 120 degrees shift, and then plus or minus 30, depending on what direction we're going and stuff like that. That's another kind of handy way to check whether or not your answer seems like it should be in the ballpark. Did the magnitude change by some factor of square root of 3? Probably all right. Did your angle change by 120 degrees plus or minus 30 degrees? Probably all right. So that was the quote unquote hard problem from homework set number 5, or excuse me, homework set number 18. That was problem 5. Have you had a chance to look over any of these others, or if you want to right now, if you want to look over any of the other problems from this one and see if anything jumps out at you that you're not sure about? And if not, we can move on to homework set number 19, which is the power related one, and look through those two, since we got a good 45 minutes left in class. They're about 35 minutes. Yeah. Okay. What? Not a problem. I just put these up the other day. You got over a week to do them. So you got over a week to ask questions and all that kind of good stuff. I can pull it up right now. Putting you on the spot since you're the only person that physically shows up to class regularly. So this first problem is you're given 2 different loads, and then the line voltage is at the load, and you want to find the line current. So I would suggest finding the total complex power absorbed by the composite load. And then you know that √3 VL IL is the apparent power. So you now figure out IL and you're done. So that one's pretty straightforward, I think. Problem 2. Pretty much, yeah. You got more loads. You have the line voltages at the loads, and you want to figure out what the line voltages at the source will be. So you'd find the complex power, total complex power absorbed by the loads, use that to figure out the line current, use the line current and the line impedance to figure out the voltage drop over the transmission line, and then add the voltage drop over the transmission line and the voltage drop over one phase of the loads to get your magnitude of your line voltage at the source. And then the power factor bit, pretty easy. The only thing I would make sure that you think about here is that when you're doing the calculation steps for part A, you're going to be figuring out effectively what the losses are, or you'll have the information to figure out what the losses are over one phase of the transmission line. But the source is supplying power to those loads and 3 phases of transmission line. So you got to make sure that you're taking into account all 3 phases of transmission line losses, if that makes any sense. So each individual line is going to have some amount of loss. They're all going to lose the same amount. So you'd effectively just figure out the loss over one line and then multiply it by 3. Problem 3 is problems 1 and 2, but backwards, because now I give you the other information and ask you to tell me what one of the loads is. Yeah, you want the average power absorbed by load 3, excuse me, and the power factor absorbed by load 3. So it's literally just the first 2 problems, but in a different order. Excuse me. Problem 4, we have a ABC Y connected source supplying a Y connected load that consumes 50 kilowatts of power in each phase at a power factor of 0.8. The capacitors have an impedance of J2, and you are asked to determine the power factor of the combined load if the capacitors are connected in parallel with the load in a Y configuration or a delta configuration. So you're supposed to assume here that the impedance remains minus J 2.0 in both cases.
Is that the power factor that they give us, or that you guys, that's like, to find people
So I don't even know that that's particularly necessary here. How I would approach problem 4. Let's see. So there's 2 different ways that you could go about this. One is that you could figure out what the total complex power absorbed by the load is, and then figure out what the total complex power absorbed by the capacitor bank is. Add those 2 together, that gives you your total complex power that's being supplied by your source, which lets you know the power factor pretty easily, right? Because it's just going to be cosine of the angle. The other way that you could potentially approach this would be to figure out what the impedance of one phase of the load is, and then put that in parallel with your capacitor. And then once you know what that combined impedance is, you also know what the power factor is, because it's just the cosine of the angle of the impedance. So either one of those 2 methods would work. I think it's probably a little bit easier to wrap your head around the, let's figure out what the complex power of the load is and the complex power of the capacitor bank is, given the voltages that we're given. But the other way works, you're just approaching it from a slightly different direction. You want to take a look at this one? Okay. So this is homework 19, number 4. So we have information given to us. We have a load, and let's see, what information do we have on that? 50 kilowatts of power per phase with a power factor of 0.8 lagging. We have capacitor impedance of negative J 2.0 ohms. And that is going to be for both Y and delta configurations. Crap. We have a voltage of VAN is equal to 220 angle 0 degrees. Volts RMS. And let's keep forgetting I don't have to switch to the other PDF viewer because I've opened it in this one. We want to determine the power factor of the combined load if the capacitors are connected in parallel in a Y configuration or a delta configuration. All right, so there is no transmission line impedance being mentioned or anything in here at all. So all right, so let's do the first case. The capacitor bank is connected in a Y configuration. So for our load, the total complex power absorbed by, we're trying to, wait, are we trying to find the power factor? Yes, okay. So because we're trying to find the power factor, it really doesn't matter if we work on a single phase basis or a three-phase basis, because it's going to be the exact same thing either way. So let's approach this on a single phase basis, all right? So our load absorbs S load is going to be P one phase divided by our power factor with an angle of inverse cosine our power factor, right? That's just like we did way back when we were looking at single phase circuits. So in this case, that's going to look like 50 kilowatts divided by 0.8 with an angle of inverse cosine 0.8. So that would be 50 divided by 0.8, 62.5 with an angle of 36.87 degrees kilovolt amperes. Let me. And now we just need to figure out what the complex power absorbed by the capacitor is going to be. And then we can just add those two quantities together. So how would we figure out what the complex power absorbed by the capacitor is going to be? Yeah, we know the voltage drop over the capacitor for a Y connected configuration. So S cap is going to be VAN times the current flowing through the capacitor conjugate, right? Which would just be VAN over ZCY conjugate, right? Because that's V times I conjugate, which is our definition for complex power. So that's going to look like the magnitude of VAN squared divided by the conjugate of the capacitor impedance. So let's see, our voltage has a magnitude of 220 volts RMS squared. The conjugate of our capacitor impedance is going to be positive J2. So 220 squared divided by 2I is going to be 24.2 with an angle of negative 90 degrees kilovolt amperes. S source is just going to be S load plus S cap. Which I get to be 51.738 with an angle of 14.896 degrees kilovolt amperes. And so our power factor for a Y connected bank is just going to be the cosine of 14.896 degrees. Cosine of the polar angle of what I have stored as Z. 966. And is the power factor going to be leading or lagging? Lagging, because the angle is positive. So that's part A. Part B. Capacitor connected in delta. Does our complex power absorbed by our load change at all? No, not even a little bit. So that's still going to be 62.5 with an angle of 36.87 degrees, kilovolt amperes. The complex power absorbed by one phase of our capacitor bank is no longer going to be VAN, right? It's going to be VAB. So it'll be the magnitude of VAB squared divided by ZC conjugate. What's the magnitude of VAB squared? Multiplied by square root of 3, right? Because we're going from a phase to a line quantity, or a line to neutral to line quantity, another way to put it. So when we square that square root of 3, it's just going to be 3 VAN squared over ZC conjugate, or 3 times 220 volts RMS squared divided by J2 ohms, should be 3 times as large, right? -72.6 angle -90 degrees, kilovolt amperes. S source still going to be S load plus S cap delta. -61.090 with an angle of -35.069 degrees. So power factor for our delta connected system is going to be the cosine of -35.069 degrees. So let's store that as Z. So cosine of polar angle of variable I have stored as Z. 0.818 is going to be this time. So in this case, we're considering this kind of a power factor correction kind of thing. Connecting the bank in Y, where we had a fixed impedance, did more, like connecting it in delta would be a huge overcorrection, right? We can see that we've gone all the way to pretty considerably leading. Right, we've made our system almost as much leading as it was lagging without the capacitor bank in there at all. So we way overcorrected. All right, let's look at problem 5. Problem 5 says we have a balanced three-phase source supplying a balanced three-phase load, which draws 20 megavolt amperes at a power factor of 0.8. The line voltage at the load is 4.6 kilovolts RMS at 60 hertz. Determine the size of the capacitors needed to correct the power factor to 0.95 lagging if the capacitor bank is connected in parallel with the load in a Y configuration and a delta configuration. So that is the exact example that we worked, except with different numbers at the beginning of class. So I feel pretty strongly that you can figure that one out. So those are our three-phase, all of the homework problems for three-phase. We've looked at homework 2 and, or excuse me, the second homework set from the three-phase stuff and the third homework set from the three-phase stuff extensively. If you want to take a look at the first homework set to see if there's anything that jumps out at you. Problem 5, which was the hard one, we actually worked in class, which means I need to either change that homework problem or change my class example that I work in class for next winter, because I didn't realize that until now. At 17 here real quick. So problem 1, we have Y connected source, Y connected load. There is no line impedances to worry about, and we just want the line current, so that's going to be real easy. And I think we did something pretty similar to that in class as well. Problem 2, Y connected source, Y connected load. We have a magnitude of line voltages. We have load impedance per phase, and we want the line currents. So I think we did something very similar to that in class also. Problem 3, we have a YY system. We are given a line current, a line impedance, and a line voltage at the source, and we're asked to find the load impedance per phase. So since it's a YY system, we know that that line current in the A phase is the same thing as the current flowing through the A phase of the load, because it's a Y connected load. We have a line voltage, we have a line voltage at the source. We know how to convert that to a phase voltage at the source. We have enough information to get the voltage drop over the transmission line, and the voltage drop at the source minus the voltage drop across the transmission line gives us the voltage drop over one phase of the Y connected load. So we now have the voltage across the load and the current flowing through the load, and the ratio of those two things is the impedance. So on a single phase equivalent circuit perspective, that's a pretty straightforward problem. Problem 4, we have a Y delta system where we are given the Y side phase voltage. We're given the impedance of the load and the impedance of the transmission lines, and we want the line currents and the line voltages. So we convert our delta connected load into a Y connected load, figure out what our line currents are using our single phase equivalent circuit, figure out what our Y connected voltage is, and then use that to figure out what our line voltage is, and then you're done. So all those are, I feel are pretty straightforward, but if you want me to work through any of them, I'm happy to help. Yeah, this is the first set out of all of this, so these are the easiest set of problems, I think, by far. So, all righty. So, unless you got anything else? All right, so I'm gonna put your test up. I hope today, if not tomorrow at the latest. I I'm also gonna get those videos uploaded. I'm gonna have to leave town. My grandfather passed away yesterday, so I have to go to New Orleans. So I'm gonna try to get everything for this class finished before I head out of town for that, which will be sometime this weekend. So by close of business tomorrow, expect all the videos to be uploaded, all of the submission portals for the homeworks and stuff like that to finally be put up. Although I think I actually have the assignment sheets up. Your test up, your place to put it and all that kind of stuff. And I'll be available to talk via email and potentially Zoom all of next week. All right, so hope you enjoyed it. See ya so dang much because I'm the program chair, so you don't have a choice in the matter.